Okay, we're going to start off today, ladies and gentlemen, and our objective is to learn about LeChatelier's principle. We talked about reversible reactions earlier in the week, in which the reactants form the products in what we call the forward reaction. The products then simultaneously form back into reactants, which we call the reverse reaction. Well, LeChatelier's principle is dealing with these reversible reactions. Now, LeChatelier, Henri LeChatelier, a French chemist, and just giving you basically the years, 1850 to 1936 was his lifespan. I don't know if that's so important for you, but just he is a French chemist. Now, LeChatelier's principle. LeChatelier's principle stated that if a stress is applied to a system that is in dynamic equilibrium, the system changes to relieve the stress. So basically what LeChatelier is saying is, if you have a reversible reaction, and that reaction's going into the forward and going into the reverse, all right, he says that if you add a stress to that particular reversible reaction, that it changes to relieve the stress. Well, let's talk about the different types of stress that can be applied to a system. We have three different types of stress that we'll be dealing with here. The three types of stress that we're going to see are changes in the concentration. It can be either the products or the reactants. Changes in temperature. We talked about thermochemical equations, in which we dealt with exothermic and endothermic reactions. So changes in temperature. And finally, changes in pressure, which I think personally the changes in pressure is the toughest one. The changes in concentration. Adding a reactant always pushes a reversible reaction in the direction of the products. Okay? Stop and think about this. If we add more reactants, wouldn't you think there would be more stuff to react that would form more products? Makes sense. So as we add more reactants, the reversible reaction will shift by making more products. Likewise, if we remove reactants, if we take reactants away, the reaction will shift towards the reactants. If we take them away, the reaction will make more of them. until we have that equilibrium set again. So if we add reactants, we drive the equation towards the product side. If we remove reactants, it drives the reaction towards the reactant side. The same principle applies when we're dealing with products. So the same thing happens when we have products. When a product is added to a system at equilibrium, the reaction shifts in the direction of the formation of reactants. When a product is removed, the reaction shifts in the direction towards the products. Well, if we add more products, it's going to drive the reverse reaction, and it's going to form more reactants. If we take away products, then the stress applied is going to cause the forward reaction, the reactants, to make more products because we just took them away. Now, a lot of the times, chemists do that on purpose. Okay? They have some desired product on the reversible reaction. But once that happens, once that reaction occurs, it shifts in the forward until we have equilibrium. So they take that product that they want, that they desire, and they remove it out of that reversible reaction. Once they remove it, it causes a stress that makes the forward reaction, that tells the forward reaction, hey, make more products. So then they get more products. It helps them to increase their efficiency. Remember when we talked about percent yield? Okay? 100% is theoretically the best you can get, but during these reactions, we're not always 100% efficient. So this is a way that chemists can help drive the equation to form more products. Okay? So basically that bottom line there, the system is changing in order to restore equilibrium. So adding the stress disrupts equilibrium, and then the system will adjust itself to restore it. Increasing the temperature causes the equilibrium position of a reaction to shift in the direction that absorbs heat. Now, if you look at this equation here that I've given, look at the forward reaction. SO2, two of them, combine with oxygen to yield 2 molecules of sulfur trioxide and release heat, correct? So the forward reaction going this way is exothermic. Now let's look at the reverse reaction going that way. What is that? 2 molecules of sulfur trioxide plus heat react to give 2 molecules of sulfur dioxide and oxygen. So the reverse reaction is what type of reaction? Endothermic. It needs heat in order to go back to the reverse reaction. So if I add heat, it's going to drive this reaction to the reverse side, towards the reactants. If I take away heat, it's going to drive this reaction to the product side, the forward reaction. Now, the rub with this is heat always going to be right here in the product side. Could heat be over here on the reactant side? Absolutely. So heat could switch sides. Okay? Oh yeah, it'll show you either heat like this, or it'll say something about kilojoules. Okay? It'll say that, you know, this reaction, for instance, we know that when we had the magnesium ribbon reacting with oxygen to form magnesium oxide, when we put that magnesium in the crucible, it wouldn't happen unless we heated it, right? So we would have to say, we could say you add heat, or we could specifically say you need this many kilojoules of heat. Okay, so it will tell you either by saying the amount of kilojoules or by saying the word heat where that heat is in the equation. Okay, you will not be able to tell if it doesn't say that. Now this slide is just telling you what I said before, that in this particular reaction that I just showed you, heat is considered a product. Heating the reaction mixture at equilibrium pushes the equilibrium towards the left. It pushes it to the reactant side. Okay? So we thus have more reactants, decreasing the products. Cooling that particular equation, cooling that equation will remove heat. So what will happen is that the reaction will adjust itself to the stress and form more products, adding that heat back in to the system until equilibrium is reached again. Pressure. Pressure changes will only affect the equilibrium of gaseous reactants and products. So I look at my equation here. I'm dealing with 3 different substances, 2 reactants and a product, all of which are gases, correct? In order for pressure to affect the system, they all have to be gases. Also, there has to be an unequal number of moles. So what we need to do is we need to eye the coefficients. I look here and I see my reactant side has 3 and 1, so my total moles are 4. My product side, my total moles are 2. Are those unequal amounts? Absolutely. So changes in pressure will affect this particular equation. Now, if those numbers were equal, if let's say we had 4 and 4, 4 on the product side, 4 on the reactant side. Would pressure affect them? No. They have to have unequal amounts. And we would agree that the reactant side has a larger amount than the product side of moles, wouldn't we? Huh? No, it's balanced. You got to have it balanced. If it wasn't balanced, it wouldn't tell us anything. All right? Now, this didn't tell us, Kyle, what it does yet. Okay? We don't know what it does yet. Oh, here we go. The very first part of this slide, it says the pressure increase will cause a shift to the right to the products because pressure decreases when going from 4 moles of a gas to 2 moles of a gas. Now, this, I told you, is confusing. The way that I think of this is 4 is bigger than 2, correct? So as I'm going from 4 moles to 2 moles, I'm decreasing, correct? So that decreases pressure, going from 4 moles to 2 moles. So if I'm at equilibrium and I increase the pressure, I add more pressure, the system wants to change to decrease that added pressure. So it changes by going to the lower side. Vice versa. I look at this and I say, okay, 2 moles going to 4 moles are increasing value, right? So as I go from 2 moles to 4 moles, I increase pressure. Okay? So if a particular system, we decrease the pressure, the system is going to adjust itself to add more pressure, so it would drive itself to the higher mole side. In this instance, the 4 moles. Now, when we talk about pressure, okay, when we talk about pressure, I can also increase and decrease pressure by changing volumes, can I? If I make my volume smaller, what does that do to the pressure? It increases it. If I make my volume bigger, what does it do to my pressure? Decreases it. So remember that, because you're going to see on WebAssign, it's going to say you've increased the volume. Well, if you've increased the volume, you've decreased the pressure. That's what they're asking you. How is this system affected by a decrease in pressure? As I increase, or as I as I reduce the volume, I increase the pressure. Okay, so when you see WebAssign talking about volumes, they're looking at you to answer how that change in the pressure due to the change in the volume. Now, once again, I reiterated down at the bottom there is no effect on a reaction when the number of moles of a gas is the same on each side of the equation. And just a final note to remember, these have to be dealing with gases with the pressure. So if there's a solid in there, there's a liquid in there, we can't tell the effect of pressure. Now, what we've done today, folks, is we've got the background details. Tomorrow, when we come in here, we're going to throw an equation up on the board, and we're actually going to walk through and see how these adjustments are being made. I don't expect you, I expect it to be very cloudy right now. Okay? I expect you to not really understand how this works yet because we don't have the whole process done. So, just hang tight. I think you'll understand it a little bit better after we discuss tomorrow's example and I actually show you how the equation is affected. Okay?